Hello and welcome to the next video in me torturing myself with Maxwell's equations. All of this is from A Student's Guide to Maxwell's Equations by Daniel Flesch. And as you might expect, as you move forward in the book, it gets more complicated. It just did. This chapter 3 is about Faraday's law, which is a moving the field induces a current in a closed loop. He's drawn a nice little diagram. I copied it right out of the book because it's just so nice. Okay, so this integral here now is a line integral. Okay, this is not a surface integral or a volume. It's always a line integral. That's the electric field, and this is the differential, the increment around the path or the line. You notice there's a negative sign here, which is interesting. And you have a time derivative of this. Now, we've seen this. This is the magnetic flux, which we studied in Gauss's law. So this part is not new. The rest of this is. And he has some nice drawings in the book, and I copied them also. So here he's showing a magnet moving in this direction toward a close. So just think of this as a wire. This is a little loop of copper wire. So this induces an electric field and a current in this wire. And the current is flowing. You see that flowing in that direction. And that's important. If it's moving away, it flows the other way. I'm not real sure why that is yet. I'm still working on that. The other way you can do it is you could rotate this loop around in a constant the magnetic field, and it would induce a current in this wire. The other one he shows is that if you had some way to shrink the loop, the size, or increase it, you could also induce a current in the wire. Um, so he gave an example in the book, and I thought it was good. So I want to actually do that before I ever get to the problems because I think it shows a lot. Okay, he said for a magnetic field given by this equation, and notice here, and he's got a z hat. That's important. Find the EMF, electromotive force, induced in a square loop of L lying in the XY plane with one corner at the origin. Now, these old equations like this, unfortunately, you run into this all the time. They give them these names. So he's saying that this here, this side of the equation, produces an electromotive force, and it's not a force. I mean, it doesn't have units of Newton, so it's not a force. It's like charge per unit area or something, but that's what they call it. So once again, the world is set up to trick students. Okay, so what I did was I drew a picture of it. So here's the way he described it. It was a square loop with one corner at the origin. Now this is the x hat, y hat, z hat unit vectors, right? So this is our unit normal. It's sticking straight up out of this thing, this square, in the z hat direction. All right. So he describes in the book that right hand side of the equation, they call it Faraday's flux rule. And it just looks like this. That's just the right hand side of the equation. EMF equals this. Now we instantly know just by looking at this diagram, we know what the unit normal is, right? N hat, it's just z hat because it's going exactly the same direction. We also know what dA is. It's dx by dy, right? So that was pretty straightforward. So we know these two things. So we can put this in our integral. And he gave us, since it's a square, he gave us the limits of integration because he said one corner of it's lying on the origin. So it's 0 to L in both directions. So we set up our integral like this. So we got our time derivative. We got y from 0 to L, x from 0 to L of this function. We dot it with the surface of the normal, which we know is z hat. And then we got our dA, which is just dx by dy. Okay, so we take the first integral with respect to y. Here's y. We get y squared over 2. Then we got our y naught. We evaluate that from 0 to L. That just becomes L squared. Thus, and we have one more integral to do. X equals 0 to L. There's no x's anywhere except here. dx, so it just becomes x. Okay, we go from 0 to L of x, and we get this. Now, we're still not done. We have to take the time derivative of this, okay, because it has a t in the function. So we take the time derivative, which is just 1, and we're left with this. So we keep the b naught, the t naught, this stuff over the y naught. All right. Now, the second part of his question was, what is the direction of current flow in the loop? Now, this part I am still a little shaky on. I'm got to do more reading on this. Okay. So he shows it here. So if the magnet is moving in this direction, the current is going to flow in the clockwise direction. And they're saying that that is opposing the direction of the electric field is opposing the direction of the field. So it produces a current in this direction, and they're going to call that negative. So that'd be the negative z hat in our case. If the magnet is moving away, it does the opposite, right? So it's going to go counterclockwise around the loop. I'm not sure the physics of this yet. I'm going to keep digging into this and see what I can find out. Anyway, that's all for now. Thanks for watching. See you later.